Hey there, and welcome to our Chapter 6 problem solving video. So today we're going to be working on 4 or 5 of the homework problems and the challenge question from Chapter 6. So the first thing we're going to look at is converting between moles and atoms. Remember that we use Avogadro's ratio to convert between these two. Avogadro's number is 6.02. For our purposes, you can have more decimals if you need them, but for our class, we're just going to use 6.02 times 10 to the 23rd power. And so moles are going to be a larger amount than atoms. So our number of moles is always going to be smaller than our atoms. So if we want to go from moles to atoms, we're going to multiply by Avogadro's number or Avogadro's ratio. If we're going from atoms to moles, from the smaller thing to the larger thing, we're going to want to divide by the large conversion factor. So we should get something that looks like this. If we multiply 0.552 by 6.02 times 10 to the 23rd, we should get this number. If we have a number that's larger than 1, we should have an exponent that's potentially larger than Avogadro's number. So this kind of makes sense for us logically, as well as if we plug into our calculator mathematically, we should get these answers as well. About twice of what a mole is should be about twice of what Avogadro's number is. 6.02 times 10 to the 23rd. 2 times that would be 1.2-ish times 10 to the 24. So a little bit less than that, a little bit less than that. Makes sense logically. You should always try to make sure that your answers make reasonable sense. You're talking about real physical things. They should make physical sense. So the next thing we can do is figure out how many moles of atoms are in each element. So we're just going to do the same thing. We have mass. We want to multiply by the molar mass so that we can cancel out. So in this case, not multiply by the molar mass, but multiply by the reciprocal of molar mass, or divide by the molar mass. So in this case, we're starting with grams. We want to cancel out grams. So we'll multiply by 1 over the molar mass, or 1 mole of zinc divided by the grams per mole of zinc. This will get us how many moles of zinc there are. And so we have way less amount of zinc than the number on the periodic table. So we should have less moles than a whole mole. So again, the number or the mass number on the periodic table is either the molar mass, the mass of 6.02 times 10 to the 23rd atoms of a material, or it's the atomic mass unit of a single atom. The mole is how we convert from the AMU to grams. Now, yes, AMUs are equal to grams, but that conversion is a lot more ugly. Instead of having 1 AMU to 1 gram via the mole conversion, using just a straight conversion from AMUs to grams with 1 atom of AMU and 1 atom in terms of grams is a very ugly conversion. So likewise, we'll use the molar mass of argon. We're just going to pull this from the periodic table. We'll go to the noble gases, go down until we find argon. We'll see that the mass is 39.95 AMU, or grams per mole. Since we're starting with grams, we want to multiply by the reciprocal of grams per mole, or multiply by 1 mole of argon per 39.95 grams of argon to get our moles of argon. Again, grams of argon will cancel out with each other, and we'll be just left with moles of argon. This is going to be a very common conversion for us for the rest of the course. We're always going to be converting from grams or moles of starting material to grams or moles of product. This is going to be one of the steps in doing that. So we could use tantalum. Tantalum might be a little bit unfamiliar, but this is a heavier metal in the cutout section of the periodic table. So we want to look there for tantalum. We'll see that the mass is 180.95 either AMU or grams per mole. Since we have grams, we're going to want to use the grams per mole variant. We can divide by our grams per mole or multiply by 1 mole per however many grams. Our grams of tantalum will cancel out, and we'll be left with just moles of tantalum. Again, lithium. do the same exact thing. This time we have a much smaller amount of lithium. Lithium has a pretty small mass, but still, we'll divide by the molar mass or multiply by 1 mole per the amount of grams of the material. In this case, lithium weighs on average 6.94 grams. The grams of lithium will cancel out and we'll be left with just moles of lithium. You notice how all the other times I put it in just standard notation, and this time I put it in scientific notation. It's because I didn't want to have a bunch of leading zeros. I would have had to have, one leading zero to the left of the decimal, two leading zeros in front of the 3. This is just a more condensed notation. At this point in time, we're only going to use scientific notation if it's convenient. Previous cases, it wasn't really convenient. It wouldn't have saved me much effort or time. Moving on to the next problem, we're going to kind of do something similar to the first problem, but a little bit different. So you'll want to notice that we have compounds instead of just elements. So remember, the molecular mass of an element is just the same as the AMU, converted for grams per mole. The molecular weight of a compound is just all of the molar masses of the elements summated up. So if we have 2 hydrogens, we're going to add the mass of 2 hydrogens to 1 oxygen, mass of 2 nitrogens to 1 oxygen, mass of 1 sulfur to 2 oxygens, the mass of 1 carbon, 2 hydrogens, and 2 chlorines. We can just summate those from the numbers we get off the periodic table. The numbers I'm going to be using here today are slightly rounded a little bit differently because I've been doing chemistry long enough to memorize what all of these are, so I use the rounded isotopic mass. But so your numbers might look a little bit different depending on what your periodic table gives you in terms of decimal places, but they should be very similar. So if we do this, the first thing you want to notice is our molar mass is always in grams per mole. We have kilograms of mass units. So we're going to want to convert this to grams from grams by dividing or multiplying by 1,000. Remember, there's 1,000 grams in every kilogram. So there has to be 112,000 grams and 112 kilograms. So that will equal, we just take the molar mass. So the molar mass of water is 18. We divide by the grams per mole, and we get moles. We can then multiply by Avogadro's number, the number of atoms per moles. That's Avogadro's ratio. To 6.02 times 10 to the 23rd molecules per atom, or atoms per molecule, or mole, sorry. Speaking a little awkwardly there. Dinitrogen oxide. We're going to have 2 nitrogens with a mass of 14, oxygen with a mass of 16. We can figure out, based on the amount of mass that we have, how many moles we have by dividing by the molar mass that we just determined. And then we can convert moles into molecules by multiplying by Avogadro's ratio. If we want to go from number of molecules or number of atoms to moles, we divide by Avogadro's ratio. And from moles to mass, we would divide or multiply by the molar mass. If we want to go from mass to moles, we divide by the molar mass. From moles to molecules, we multiply by Avogadro's number. So again, we'll figure out what our molar mass of sulfur dioxide is. Sulfur weighs 32, oxygen weighs 16, so this total molecule has a molar mass of 64 grams per mole. If we have 156 grams, well, they gave us moles, so we can multiply moles by the grams per mole. Moles will cancel out, and we'll just get grams. I apologize for leaving out the gram unit. You should always include your gram units. If we want to go from moles to molecules, moles are a smaller number than molecules. It's a larger unit, so you'll have smaller numbers. So we need to increase the number we have for molecules from moles. So we'll multiply by Avogadro's ratio, or multiply by 6.02 times 10 to the 23rd. We should get these answers. For methylene chloride, this is an organic molecule. It has different naming procedures than the binary compounds that we've been talking about so far. At the very end of the class, we might talk about some of these naming procedures. You're not going to be responsible for them. I will never ask you to name an organic compound, but this is called methylene chloride or dichloromethane, 2 names that mean the same thing. They gave us the amount of moles, so we can calculate its molar mass by taking 12, which is the mass of one carbon, adding it to 2, which is the mass of 2 hydrogens, adding it to about 70, which is the mass of 2 chlorines. Chlorine's mass is 35.45, so about 71 for 2 chlorines. I don't know off the top what that molar mass is, but you can plug that into your calculator. If we multiply by the molar mass, moles by the molar mass, we'll get the amount of mass in grams. If we multiply the amount of moles by Avogadro's ratio, we'll get the number of molecules. So the next thing we can do is kind of the same thing, but now we're going to determine from moles of a given species to moles of the atoms in that species. So in 4.67 moles of water, there are more than 4.67 moles of hydrogen because for each molecule, there's 2 hydrogens. So for however many hydrogens or however many of whatever designated atom, in this case, we're always looking at hydrogens, we're going to multiply the number of moles by the amount of hydrogens in that molecule. So for the first one, we're going to multiply by 2 because there's 2 hydrogens. 4.67 times 2 gives you 9.34. Notice we went from moles of H2O to moles of hydrogen. It's not a molecule. We don't have an H2 behind here, so it's moles of hydrogen atoms is how we would say it. Likewise, 8.39 times 3, because there's 3 hydrogens in ammonia, gives us 25.2 moles of hydrogen atoms in 8.3 moles of ammonia molecules. We could do the same thing with hydrazine. Again, organic molecules, you don't need to know how to name them. This is called hydrazine. There are 4 hydrogens for every 1 mole or 1 molecule of hydrazine. So we will multiply however many moles we have, 0.117 by 4, and we'll get 0.468 moles of hydrogen atoms and this many moles of hydrazine molecules. The last one we'll do is decane. Again, organic molecules, don't need to name them. There's a whole bunch of hydrogens in there. There's 22 hydrogens per 1 single molecule. This is a lot bigger of a molecule than we've really talked about so far. So if we have 35.8 moles of that, that's a good number of moles and quite a large number of hydrogens per mole. So we're going to have a huge number of hydrogen atoms. So 35.8 moles of decane has 788 moles of hydrogen atoms in it. Moving on to the last homework problem, we have our composition of the chemical compound. So we have a compound containing nitrogen and oxygen, and we don't know exactly what the relative nitrogen and oxygen composition is. So what we want to do is we want to divide both of these numbers by their molar masses. We will divide nitrogen by its molar mass, 14 grams, oxygen by its molar mass, 16 grams per mole. Again, the numbers that you get on the periodic table will be slightly different because I'm rounding to the wholest number isotope, but our numbers should be very, very similar. We're going to calculate the empirical formula, so this might be slightly different than the molecular formula. We would need other information, the percentages of different things to figure out what the molecular formula was from the empirical formula. If we knew how many atoms were in the molecule, that would help us determine it. Would be one source of information that it could be. But that's not this type of problem. We're just figuring out the empirical formula. So we'll divide each one by its molar mass. And we're going to try to get those ratios or decimals into whole numbers. So we take nitrogen divided by the molar mass of nitrogen, or multiplied by its reciprocal. That'll give us the moles of nitrogen and oxygen, respectively. We want to normalize whichever one is the smallest number. Normalization means make it equal 1. In order to make any number equal 1, we just divide by that same number, or multiply by 1 over that number. With dimensional analysis, we only like to do multiplication so we can cross-cancel. In this case, we're going to cross-cancel our number, and we're going to be just left with 1 mole of nitrogen. We're not crossing out the units, which is our normal go-to. Now we're crossing out the number to normalize the number to 1. We have 1 mole of nitrogen. If we do the same thing to oxygen, because 0.127 is smaller than 0.53, we get 1.99 moles of oxygen. Now, that's so close to 2 that we're going to round it up to 2. Same thing with the percentage problem, relative abundance problem in Chapter 5. It was so close, it was just 0.01. It was just 1 decimal place off of being our exact number. So we're just going to round up because that's within the error of whatever instrumentation we're using. So we would get nitrogen dioxide as our empirical formula. Now that could be the molecular formula. It could just be the empirical formula, and we'd need some, scalar multiple of that. It could be dinitrogen tetroxide. It could be trinitrogen hexaoxide. That's unlikely because that's not really a stable compound, but you guys aren't really expected to know what are and are not stable compounds. Now to our challenge problem for Chapter 6. So this is the problem you can expect to see on your exam, or at least another variation of this problem. So what we have here is we want to figure out what the concentration of a given ion is in a molecule. So this is an ionic compound, sodium sulfate. When this dissolves in water, each of the ions will dissociate from each other and be solvated by the water molecules. We have a couple images of this that kind of show how things dissolve in solution. That won't be showed here. Make sure you reference the lecture or talk to me in lab about that. But for this type of problem, we want to figure out how many of these sodium plus ions are in 5 liters of solution, but we don't want to know that in terms of moles, which is what was given to us. We want to know it in terms of kilograms per liter. Moles convert to grams per moles via our mole ratio. So we're going to have to convert our grams into kilograms at some point. So the first thing is we want to take our given piece of information, 5 moles of sodium sulfate. We want to find the molar ratio of sodium sulfate to sodium ions. This is called a mole ratio. So we have 2 moles of sodium ions in every 1 mole of sodium sulfate. That would give us 10 moles of total sodium ions in every 5 moles of sodium sulfate. We then want to convert to grams using our molar mass. We can convert by multiplying by the molar mass. Moles of sodium ions will cancel out, and we'll just have grams of sodium ions. Once we have grams of sodium ions, we can then just do our metric conversions from Chapter 2, 1 kilogram in every 1,000 grams, or vice versa, depending which way we're converting. Grams will cancel out, and we'll be left with 0.23 kilograms of sodium ions. However, that's not our final answer. We wanted to find kilograms per liters. We have kilograms. We were given liters. So now we're just going to take our mass, divide it by our volume, and we'll get our concentration, or the density of sodium ions is another way to think of it. This would be our final answer, rounded to the same number of sig figs that, well, actually not rounded to the same number of sig figs. If you have any questions on this type of problem, make sure to ask me in office hours or lectures. Again, if this was a sig fig problem, I would designate that we needed sig figs. There would have only been 1 sig fig in this problem, but that would have been a little less informative. I wanted to give you an extra decimal place just so that you could reference it for your calculations. But reach out to me if you have any questions on these type of topics. Otherwise, I'll see you in lab this week, and you can wait for next week's lectures.